Hi, I'm Jeff Perry, the manager of the WEBENCH team at Texas Instruments. Today I'm going to talk to you about the WEBENCH Power Designer, and we're going to go through a basic overview. We're going to be discussing the WEBENCH Power Designer, and this is a tool that designs power supplies and system power architectures. But we also have the LED Designer tool, which allows users to create LED driver designs and also do LED architectures where you can array out the entire LED array and heat sinks. We have a Sensor Designer tool that allows the users to design sensor analog front ends. We have our WEBENCH Active Filter Designer for active filter design and simulation. We have the WEBENCH Easy PLL Designer that allows users to design loop filters for their PLL circuits. And then we also have the Amplifier Designer, which allows op-amp design and simulations. WEBENCH is fundamentally a end-to-end design and prototyping system. In the first step up here in the upper left, the user would simply enter in their input requirements. So for power, this would be the input voltage, the output voltage, and the current. WEBENCH then crunches those numbers and presents a list of alternate solutions that the user and recommended solutions that the user can choose from. In step 2, the create design step, the software calculates the bill of materials, and this includes efficiency, operating values, and graphs to visualize the design. In this step, the user can optimize the design for small footprint, high efficiency, or low cost. In step 3, the user can analyze the design. This allows the use of SPICE simulations to do dynamic analysis of the design, and also thermal simulation to view thermal issues across the board and provide solutions for that. The last step is the build it step, and from this step you can get custom prototype kits sent to you overnight. There's really 3 levels to the WEBENCH Power Tool Suite. I'm going to start out by talking about the WEBENCH Power Designer, which is a single power supply design. How do you get to WEBENCH? Well, simply go to texasinstruments.com, or ti.com I should say, and there will be a panel on the right side that allows you to enter in your WEBENCH design parameters. There's different tabs for power, also for the FPGA microprocessor architect, the sensor designer, which I talked about, and the LED designer. If you're interested in going to a specific part number, you can go to the product folder for that part, and there'll be a WEBENCH panel there also. In the past 12 years since WEBENCH was invented, we have covered a wide variety of parts and part space, I should say. At this point, WEBENCH can go all the way up to 40 to 60 amps using some of our interleaved controllers. That's for the output current. For the minimum output voltage, WEBENCH goes down to 0.6 volts with several different parts. The maximum input voltage is all the way up to 100 volts, and the minimum input voltage can go all the way down to 1 volt. So what we've tried to do in WEBENCH is cover a lot of ground to provide the most solution space for our users. WEBENCH also has multilingual capability. This includes Japanese, Chinese, both traditional and simplified, Korean, Russian, German, and Portuguese, and we're continuing to add additional languages. To change the language, simply start up WEBENCH and go into the upper right section of the interface and click on one of the links. The WEBENCH Navigation primarily consists of icons at the top of each screen. Right now I'm showing you the new screen in WEBENCH. This allows you to change and update your selection parameters. It also allows you to get to the other WEBENCH tools, and as I said before, this is the Power Supply Design tool for single power supplies. You click on the LED tab right next to the Power tab, you'll get into the LED Designer, also the LED Architect, the Power Architect for system power supply design, which I'll talk about in a little bit, the FPGA microprocessor designer, and also the hot swap controllers. Once you've created your design, this is the WEBENCH dashboard that you'll see. And let me walk through each one of these different areas. In the upper left, you have the WEBENCH optimization knob. And this allows the user to optimize the design for high efficiency, small footprint, or low BOM cost. Next to that, we have our operating values charts. And this allows you to visualize the behavior of things like efficiency, duty cycle, power dissipation, over the load current, and over the different input voltage ranges. Below that, there's actually a table of operating values, and that allows you to look at the numbers in more detail if you'd like to. To the right of that, we have the schematic, obviously a key component of any design. And below that, we have the bill of materials. In the bill of materials, you can either update your components with our picking from our library of over 25,000 passive components, or you can enter in custom component values if you have a specific component that's not in the library. In the upper right is our design optimization graphs. This allows you to look in one place at the effects of the optimizations on things like power dissipation, cost, efficiency, and footprint. And so that saves you the time from turning the knob back and forth, and you can visualize everything in one spot. In the lower right is the build it and reporting area. And so this allows you to do things like get a PDF report, do downloads of CAD files, and share the design. As I mentioned earlier, up at the top are the WEBENCH navigational icons, and that allows you to get into these various steps, or you can just click on the box here to open that up. I wanted to additionally mention the WEBENCH simulation steps. So by clicking on the sine wave or the thermometer there, you can get into the WEBENCH electrical simulator or thermal simulator. Okay, let's talk a little bit more about electrical simulation. As I said before, if you click on the sine wave icon up here, it'll get you to the electrical simulation page. In the upper left, you have a drop-down specifying the simulation type. And there's 5 different simulation types in WEBENCH typically. One of them is a Bode plot, where you can check the loop gain stability. Another one is line transient, to check for input excursions and how that affects your output voltage. Of course, we have load transient that allows you to change the output current and put a spike on the load and see how that affects the circuit. We also have startup simulation and steady state simulation. Once you've selected the simulation type, simply click the green Start New Simulation button. Simulations take on the average somewhere between 1 to 4 minutes. When the simulation is done, the waveform will pop up on the right side in the waveform viewer. This has all the typical waveform controls such as zoom. If you click and drag your mouse down and to the right, you can zoom in. You can add additional waveforms from a selection list here at the bottom. This is a Bode plot. We only have gain and phase. But typically in the time domain simulations, we'll have the various nodes in the circuit where you can probe voltage and current. Once you run one simulation, you can change the circuit by clicking on a component in the schematic or going to the BOM page and selecting an alternate, and then run additional simulations and overlay the plots together. That allows you to compare changes in your design as you go through the design process. WEBENCH thermal simulation is another feature. This allows you to identify and correct simulation issues. Things that you can change include the copper thickness, airflow, and also the board orientation. This is a typical thermal simulation result. On the left side, there is a simulation that was run using 1/2 ounce copper thickness. And in this case, the low side FET is 117 degrees C. And you'll note that simulation can give you the effects of components that are next to each other, which is something that's not possible to do with theta JA. And so in this case, we've got a high side FET and a low side FET positioned relatively close to each other. And you can see there's some co-heating there of the two. The next simulation over here shows what happens when you increase the copper thickness to 4 ounces, and that dropped the FET temperature all the way down to 68 degrees C. And so this not only allows you to identify problems, but also helps you solve thermal issues. The Build It step, which you can get to by clicking the shopping cart icon in the navigation bar, allows you to order a custom prototype kit. This includes the bare board and parts, and so you do the soldering, but allows you to come up with a prototype very quickly because these kits can be shipped overnight. When you're done with your design, we have a PDF report generator that includes the schematic of the design, the bill of materials, and also the operating values. And we know that documenting your design is very important, and so this allows you to do that very quickly and easily and save that for future reference. The design is also saved for you on the server, so you can come back to it later. It is password protected, and you can come back at a later time and look at designs that you've already done and optimize them and reuse them again. You can also share designs with other team members or management by clicking on the Share Design button in the upper right of the navigation bar. And once you do that, it will ask you to enter in the email address of the recipient, and it'll send them an email, and once they click through that email, they will get a copy of the design. All right, now I'm going to cut over to do an actual demo using the WEBENCH online software. Here we see the Visualizer page, which is what comes up when you launch the software initially. For this case, I've entered in 14 to 22 volts for my input voltage range. I've entered in 3.3 volts for my output voltage, and I've entered in 2 amps for my load current. The ambient temperature has been set to 30 degrees C. Below this, we have a list of recommended solutions. I'm going to click the adjustable switching frequency button, or a checkbox, so I can choose parts with adjustable switching frequency. For this demonstration, I'm going to use the LM22670. Okay, here's where WEBENCH is going to go off and actually calculate the bill of materials and the operating values for the design. And you can see here we're on the WEBENCH dashboard. Okay, let's talk a little bit about design optimization. As I said before, you can actually optimize this design to go for small footprint, low BOM cost, or high efficiency. Now our initial results here are a footprint of 454 square millimeters. What this is the square millimeter area of all the components in the bill of materials. It does not include the actual PCB area that you'll end up with, but it's a good figure of merit to use to compare different designs together. The BOM cost is $3.40. This is the 1,000-piece pricing, so it's a fairly low volume pricing. Again, this is good for comparison of different designs together, but your actual pricing will likely vary from that depending on your volume. To the right of that, we have the efficiency, which in this case is 79%. Now, if we want to optimize this design for high efficiency, all we have to do is click on the optimization knob here and click on the number 5. WEBENCH will go off and actually run a suite of designs and optimize them for you, in this case by fundamentally lowering the switching frequency. This reduces the AC losses in the circuit and tends to improve efficiency. And we can see here that the efficiency now has gone from 79% up to 85%. The BOM cost has also gone up, and the footprint has gone up. So that's really the fundamental trade-off. Now if we want to go to small footprint, we just click on the 1 here in the optimization knob, and WEBENCH will optimize it for small footprint. This time it's going to raise the switching frequency, which typically allows the inductor and other components to be smaller, but it's going to hurt our efficiency a little bit. So our footprint now is at 296 square millimeters versus the initial value of 454. Our BOM cost is $3.72, and our efficiency now is 75%, which has dropped down quite a bit from that peak of 85%. Let's go to low BOM cost. What this does is it continues to use a relatively high switching frequency because smaller components tend to be cheaper, but it also looks for components that are simply low cost. And we did that. The cost here now is $3.30. The efficiency is kind of in the middle of the road here at 78%, and the footprint is in the middle of the road also. As I said earlier, if you'd like to look at these things in more detail, you can click on that optimization panel, and this will show you what's happening with things like power dissipation versus the optimization number here on the x-axis. You can see as we go to higher efficiency designs, our power dissipation comes down. The switching frequency shown here in green is being minimized over that optimization. And here's a graph of the efficiency in green and the footprint in orange. And you can see here that the efficiency is going steadily up along with the footprint. The BOM cost over this optimization range is shown here, and you can see it dips primarily for optimization setting 2, which is the low BOM cost portion. Now I'd like to talk a little bit about the WEBENCH Visualizer. This is a technology that allows you to look at many designs up front, and for a company like Texas Instruments that produces, dozens of different solutions, it can be hard for even a power supply expert to determine which one's going to be the best one for their application. Here's the visualizer screen. On the right side, you'll see a table of recommended solutions. Now, the important thing to realize here is that all of these solutions are dynamically calculated based on your inputs. And the 3 key columns we're talking about here are the BOM footprint, the BOM cost, and the overall efficiency. The footprint and cost are not just the IC that's used for the power controller. This is the entire BOM, including the inductor, capacitors, diode, and the same thing for the cost. It's the entire BOM cost. Since these are dynamically calculated, it allows you to easily compare different solutions to each other up front without having to go through and create individual designs. On the left side, we have our visualizer chart, and this shows you a graph of footprint, efficiency, and BOM cost, so you can see the results visually. In the upper area up here, we have filters, so you can filter on different features, and we also have slider bar filters, so that you can filter on different criteria. This is a blow-up of the plot, and so again on the x-axis here you'll see the efficiency, and on the y-axis you'll see the BOM footprint. The bubble size here is the BOM cost. And so what we see here is a question would be, why is there such a wide diversity of efficiencies and footprints? And you can see here that this varies really on the technologies that's used in the power supply itself. Over here on the right we see synchronous controllers, which tend to be higher efficiency, but perhaps a little more difficult to design with. Here we have synchronous integrated switch parts, which tend to have the benefits of higher efficiency, but they're easier to design with because they have onboard FETs. Here we have asynchronous integrated switch parts, which tend to be the easiest to design with, and their efficiency and footprint tends to be a bit more of a compromise. And then here we have some older technology parts, which I like to keep into the tool to show that as time goes on, parts do get better in performance. Okay, let's cut over to a live demo here to show how this works. Okay, I've clicked on the visualizer icon up here in the WEBENCH navigational bar. And what I'm going to do here is I'm going to take a look at the visualizer graph. You can do that by clicking on this little square here, and you can drag this guy up here with a little drag bar. Now here it shows you all of the different part combinations that satisfy our criteria here of 14 to 22 in, 3.3 out at 2 amps. If you move your mouse in, you can hover over the different parts. And so over here we see we have a part that's all the way up at almost 95% efficiency. And the footprint is relatively good. The cost is about $3. Here's the recommended part, which has an 82% efficiency. The cost is $3.37, but it's got a very low footprint of 272. And so WEBENCH, through a weighted sort algorithm, is able to prioritize and characterize the recommended part for you. Let's go through and take a look at how you can filter the results. Let's say you have a minimum efficiency requirement of 85%. So you can change the slider bar here to go up to 85%. And as you do that, you can see the plot on the left is changing. Okay, so this limits it now to the parts that are only greater than 85%. Let's say you've got a BOM cost limitation. And so as you drop this guy down to, let's say, your BOM cost is $4 limitation, say, okay, those are the parts that meet that criteria. And then within there, I want to look at parts that have a peak-to-peak output ripple of 50 millivolts or less. And so this filters that list down to show you that these are the best parts that satisfy your specific criteria, and then you can feel free to choose these and create a design from them. So So what we've seen here is the ability of WEBENCH to show you multiple designs, up to dozens of different designs calculated in a matter of seconds, and show you that calculation up front and how you can compare them together very easily. Let's talk about the highest level of the WEBENCH pyramid here. We talked about the individual power supply design. We talked about the WEBENCH Visualizer, lets you compare individual power supply designs up front. And let's talk now about the highest level, which is the Power Architect tool. The Power Architect tool actually allows you to design power supplies for entire systems, for things that include things like FPGAs with multiple loads and processors with multiple loads. And as you can well imagine, some of these systems can have 8, 10, or more different voltages and currents that have to be satisfied. So even using WEBENCH Designer, that can be a bit of a task. What we did here is we said, let's combine the requirements for all the supplies into one big system and use WEBENCH to its best capability to design each one of those supplies individually and fit them together into a power supply tree. This is a screen that shows the system level visualization. So again, like the single power supply visualizer, on the x-axis we have the system efficiency, in this case going from 76 to 94%. On the y-axis we have the BOM cost, or BOM size, for the entire system. The BOM size here goes from 8,000 square millimeters down to 2,000, so you can see the whole magnitude of that has changed quite to the system level. And then the bubble size is the relative system cost again. The colors here are the different design optimizations. And so the blue over here on the right is the high efficiency. And so then we go from the knob setting of 5, the light blue is 4, green is 3, and so on and so forth till we get to the small footprint stuff down here in the lower left. And you can see this fundamental trade-off where if you want to have high efficiency, it's very difficult to get small size, and vice versa. If you want small size, the efficiency usually suffers. And that's accomplished through the optimizer dial in the upper left. On the right side is the power tree that's been created. Now the WEBENCH Power Architect will look at several different power trees and show you the results. Here's an example of one. And so for each one of these things we have the power supply source on the left, that's your input source. Then we have a supply for each one of the elements of the tree. Now this is a tree that has an intermediate rail that's feeding a 12-volt supply, and then the point of load supplies are feeding off of that to go to the lower voltage loads like the 1.25 volt here, 3.3 volt here, 1.8 volt, and 2.5 volt. Now what WEBENCH does to handle this after it's created these power tree options is that it'll run a visualizer plot on each one of those supplies and give you the best recommended supply depending on where your optimization knob is set. So here, for example, the 12-volt supply, I've got a recommendation there. And then for each one of the point of load supplies, it runs those on the visualizer and gives you a recommendation for each one of those. Now this can take a little bit longer to run. This can take anywhere from 30 to 60 seconds. But in so doing, it'll give you a complete solution to your entire power supply system. I want to summarize what we've talked about here. Number one, WEBENCH is an end-to-end design solution. It has online selection, simulation, and prototyping. It also allows dynamic design optimization based on size, cost, and efficiency. We talked about the WEBENCH Visualizer that lets you view dozens of designs at a time to get the best solution for a single power supply. Each design is optimized for efficiency, cost, and size depending on your preferences. Lastly, the WEBENCH Power Architect allows system-level designs for complex multiple load applications. It provides different rail architectures, and each system can be optimized for efficiency, cost, and size. And overall, WEBENCH Tools can save you a lot of time in your next power supply design. So I would encourage you to use the award-winning WEBENCH tool. Just go to ti.com/WEBENCH. Thank you for your time.